With no further ado, let me introduce DillonFranke, who's going to be giving us some cool information about how to look at Mac OS. So please, let's put our hands together and welcome Dillon.
All right. Well, thank you all so much for being here Sunday morning. Really appreciate you showing up so early after, I'm sure, a good Saturday night. Really excited today. This is my first ShmooCon. It's a pleasure to be here, and it's already becoming one of my favorite security conferences. So thanks to everyone that I've met. Everyone's been just so great, and it's been a lot of fun so far. Quickly, I'll just discuss who I am, give you a little background about myself. Currently, I am a proactive security consultant at Mandiant. We were just acquired by Google Cloud last year, so that's been kind of a whole process, but been really good overall. As well as just finished a job rotation with Mandiant's Flare Offensive Task Force. So this is a reverse engineering team. We do a lot of malware reverse engineering, as well as searching for O-days and exploits used in the wild. And then also performing kind of some additional new security research. In my role as a proactive security consultant, I'm more focused on pen testing and red teaming. So my kind of main focuses are application security, source code reviews, and embedded device assessments. Before that, I have a bachelor's and master's degree in computer science, focus on computer and network security, as well as low-level systems engineering. And hobbies, enjoy playing guitar. I'm from San Francisco, so really enjoy cycling around the Bay Area. And, of course, hacking. So I'm excited to give this talk. I invite you to join me today as I dive into kind of my process that I've spent over about the last year off and on looking for low-level vulnerabilities in Mac OS, specifically dealing with Mach IPC mechanisms. This research is definitely still in progress, but I really hope there's a little bit of something for everyone in this talk. We're going to start kind of with a crash course on fuzzing and Mac OS, as well as the IPC mechanisms that it uses. And so really, if you're just getting into vulnerability research and fuzzing, I hope to really build up kind of that knowledge for you. Then we're going to jump into the memory corruption attack cycle that I've gone through in this research, and kind of just talk about some of the pitfalls that I've come across, some of the difficulties I've had, and hopefully inspire you to look at some interesting new attack vectors and fuzz them. I'm then going to talk about some of my next steps that I'm excited about in this research, and then we're going to have some Q&A. So without further ado, let's go ahead and jump into a bit of background knowledge here. So just as a very basic definition, let's talk about what fuzzing is. My definition of fuzzing I like to use is sending unexpected inputs to a system in the hopes of making something unexpected happen. So pretty simple, where a lot of times this just looks like random data. When we get more sophisticated, we start looking at grammars and building more kind of complex messages to send to a system. But at its core, this is what fuzzing is. What is an attack vector? So an attack vector is the channel in which we send an input to a system. Therefore, it's the way in which we fuzz, the communication channel to fuzz. And a couple examples, attack vectors, you can really get creative with this. The world is really your oyster, and I urge you to do this when you're thinking about what is actually attackable. So if we just think of a laptop, for example, there's so many different ways to attack it. We can look at Bluetooth connections and how incoming data is parsed, maybe from devices connecting to it. We can look at inter-process communications like we're going to be doing today. We can even look at like push notifications coming in to a mobile phone maybe. Peripherals that are connected, maybe a device driver that they use. And of course wireless connections. There's really an endless amount of ways that you can attack a system. So just as a couple of examples of attack vectors. I just have a couple examples here. For example, if you're looking at Adobe Acrobat, PDF preview and viewing and editing application, the attack vector here might be opening PDF functionality. So an input then might be a maliciously crafted PDF. But we don't always just need to have an attack vector that's opening something with a program. I think in fuzzing a lot, we think of just opening AFL, attaching it to a program, and sending a bunch of inputs to it. But we can really fuzz anything. We can fuzz parameters in a web application like you see here. We can even fuzz, like I mentioned, Bluetooth data incoming to a smartwatch. So really the bottom line here I'm saying is get creative with this. And I tried to think out of the box when thinking about what I wanted to fuzz. So why do we even want to perform fuzzing, you might ask? And that's because pretty much everything is built on top of memory unsafe languages, aka C and C++, and we want to try to send inputs that cause that C program to crash. And depending on the crash that we're able to trigger, we might be able to exploit a buffer overflow, a heap overflow, a use after free, a double free, or a memory leak, which could give us information that we can use to bypass ASLR. So here's just an example, kind of tying all these concepts that we've discussed together. This is an Adobe Acrobat use after free vulnerability. It resulted in RCE, remote code execution. The attack vector here, as you can see, is opening a malicious file, so that maliciously crafted PDF. And if we look at the description, there's an existence of an object prior to performing operations on the object. It's not validated. So this is a classic use after free vulnerability, and this was discovered via fuzzing. So there's a lot of really interesting research that fuzzing can produce, and often we catch very critical vulnerabilities in high-profile software like this. So there's two main types of fuzzing that we're going to be discussing today. The first is mutation-based fuzzing. So this is when we have a bunch of existing inputs, and these might be inputs that we've seen in the wild. They might be known good inputs. They might be like a bunch of valid PDFs that we want to send to Adobe Acrobat, for example. And mutation-based fuzzing is modifying those known good inputs and then sending them to the program and seeing what happens. On the other hand, we have grammar-based fuzzing, which is going to be generating inputs based on some sort of syntax or rules that we use to define the structure of a valid input. So an example of this, maybe you're fuzzing a browser and you want to try to generate interesting JavaScript payloads. You might write a grammar for what is valid JavaScript syntax and then generate a bunch of different JavaScript functions and objects based on that grammar. Today, though, kind of based on the research that I did, we're going to be looking at mutation-based fuzzing. So taking those existing inputs and then modifying them and seeing what happens. Okay, so we've established what fuzzing is. We're going to jump in now a little bit to a little Mac OS background. So at a basic level, what is the XNU kernel? So this is the kernel that powers Mac OS. Stands for X is not Unix, which is kind of funny. There are three main components of it. So there's the Mach layer, which is responsible for a lot of low-level tasks. So this will be things like thread management, inter-process communication, and memory management. You have the BSD layer, which is going to be a bit higher level. That's going to be more file system network-related tasks. And then you also have IOKit in the XNU kernel, which is a framework that developers can use to create drivers. Today, we're going to be really focusing on this Mach layer. So we're kind of targeting the lowest layer in the Mac OS kernel, and specifically looking at inter-process communications. So inter-process communications, why do we need them? Because processes need to talk to each other. They need to talk to each other for a lot of different reasons. Sometimes this is thread scheduling. Sometimes this is alerting another process that it's finished with a task. Sometimes it's used for remote procedure calls. There's a lot of different reasons why processes need to talk to each other, but they do. And there's a lot of ways they can do it. So on Mac OS, I've listed a few here. Mach messages are going to be really what we're looking at, and these are the lowest level IPC mechanism that exists on Mac OS, and they're actually the basis for many of these higher level mechanisms that you see here. So they're kind of the building blocks. So by targeting that lower level mechanism, my hope was that we could cover kind of all of our bases here on these other IPC mechanisms. Okay, so looking a little bit more into Mach IPC and how it works. First, let's define what a Mach port is. It's pretty simple. A Mach port is just an IPC message queue, and it's managed by the kernel. So you can really think of this as just kind of a letterbox that's processing incoming messages, and then there's messages being sent to it, and then there's messages being dequeued or read from it. With Mach ports, there's this notion of a port write. So this is a handle to a port that allows some operation on that Mach port. So typically, this is either the ability to send messages to the Mach port or receive from the Mach port. So here's the most three common port writes that you'll see. A receive write allows you to receive a Mach port's message. A send write allows you to send messages to that Mach port. And send once, which allows you to send just a single message to a Mach port. Then you lose that write. And you can actually, if you have a macOS operating system, you can use the LSMP tool that you see here to view information about Mach ports. So here we've done that with the KEXD process. And as you can see, there's a ton of different Mach ports that are being utilized by it. We see mostly send Mach ports with a send write, and we do see a few with a receive write, which is pretty typical. Okay, let's talk about how we establish a connection via Mach IPC to get these processes talking together. So there's this notion of a bootstrap server, and this is actually stood up by LaunchD, if you're familiar with macOS. It's one of the first processes that gets launched on Mac, and it essentially sets up this bootstrap server, which will help establish connections with other Mach ports. By default, any process can send. They have a send write via Mach to this bootstrap server. And because of that send write, the bootstrap server can help broker and negotiate communications with other processes. I'm also going to define here what a Mach service is. So this is just a Mach port like we defined before, but it has a specific name that is registered with the bootstrap server. So the bootstrap server, let's take the example COM Apple Moose here. If we have that service, the bootstrap server will have a mapping of that to a specific Mach port, and when someone looks up the name COM Apple Moose, the bootstrap server will be able to say, all right, here is that Mach port, and here's the specific send write to that service. So here's just a quick example of how we would communicate with the service. Let's say Alice allocates a new Mach port with a receive write. Then she's going to use the bootstrap server. She's going to register COM Apple Moose with the bootstrap server. And by doing that, she's giving the bootstrap server a send write to that port that she allocated. And she has a receive write to it. Then let's say Bob asks the bootstrap server for the service COM Apple Moose. And the bootstrap server is going to say, all right, I will give you a copy of the send write for Alice's Mach port. Now that Bob has that, he can use that send write to send Mach messages to Alice's Mach port. Okay, so now we know how the connection gets set up. What do these Mach messages actually look like? So a Mach message is a struct that's used to exchange data between Mach ports. And you see a bit of a diagram here. We won't dive too much into this. The main things kind of to point out here is the message size, which is in the Mach message header, the remote port, which is going to be the Mach port that we are sending to, and then the message body here, which is going to be typically binary data that the receiving process knows how to interpret. So there's not a lot of specification of what can or can't be sent in this body. There's actually no limit to the amount of data that you can send in the body either. It's really for the receiving process to kind of define and to expect from the sending process. So messages are sent and received via the Mach_message function, API on macOS. And so this is used for sending and receiving messages. The option here, the second field, will specify whether we're sending or receiving a Mach message. And then this Mach message header T type is our message header, which we see on the right here. So this is going to contain all of the information, including the message body. Okay, perfect. So we have gone ahead and defined what fuzzing is. We've defined a little bit about macOS and how IPC mechanisms work within it. I'm now going to talk through my process for attacking IPC mechanisms on macOS. The cycle that I went through here was first identifying an attack vector, which we've done a little bit by identifying we want to fuzz Mach IPC, but can we limit the attack vectors that we're looking at, and specifically the processes that we're targeting. Then we're going to look at how do we generate a corpus of inputs. So a corpus, as we'll talk about in just a minute, is just a grouping of valid inputs that we've seen and that we know is going to be processed in some way by the receiving process. Then I'm going to talk a little bit about how I wrote a custom fuzzing harness to send Mach messages to processes I was interested in fuzzing. Then I'm going to talk about the actual fuzzing process and producing crashes, as well as generating code coverage. And then finally, I'm going to talk about how do we identify what is a relevant or meaningful crash. Then we're going to get into kind of next steps and questions. Okay, so let's talk about how we can abuse Mach messages. The first major way, and this is not new research here, this has been done for many years, but Mach messages can be abused to create a sandbox escape scenario. So let's say you have found remote code execution in Safari, a web browser. That process is going to be sandboxed nowadays. That wasn't always the case, but now that remote code execution on Safari is not super meaningful because you're still within the sandbox. You can't access the user's files, you can't install persistence mechanisms, you can't do anything really. So Mach IPC exists as a channel here because from that web browser process, we might be able to send Mach IPC messages to a message handler that's outside of the sandbox. And by doing that, if we can corrupt the message handler and the underlying process, we have effectively escaped the sandbox and turned what was a pretty mundane Safari RCE into a full system takeover. The other way that Mach messages can be abused is for privilege escalation. So let's say you have an unprivileged process running just as the local user. You can perform the same sort of attack by targeting the message handler and take over a privileged process. So these are kind of the two ways Mach messages have been abused in the past. I wanted to focus on looking at sandbox escapes to kind of hone in on my attack surface a little bit. And so to do that, I used a tool that's publicly available by Jonathan Levin. If you know anything about macOS research, he's very knowledgeable in the space, and I've read a lot of his material. He's got some great tools as well. One of these is SBTool, and this tool uses macOS's built-in sandbox check function, and what you can do is essentially attach it to a process and say, I want you to check what I'm able to do from this process. So here we're attaching to this process, 2813, this was Firefox, and I'm saying, which processes or services can I send Mach messages to? And it'll actually go through and generate a list of services I can interact with. So this helps a lot because we go from honing in our attack surface. We're looking first at all macOS processes that receive a Mach message, which is pretty much every process on macOS. Then we're just looking at processes with a Mach service. But by using this SB tool, we're able to look at processes with a sandbox allowed Mach service. And that really helps us hone in that attack surface. Just want to point out a couple of previous researches that have gone on kind of in this same vein of Mach privilege escalation and sandbox escapes. One, I had the privilege of seeing a couple years ago at Black Hat about using Mach messages and IPC mechanisms to break out of Chrome. And then some work that's been really inspirational and helpful to me was I believe a 6-part series blog by Ret2 Systems which talks about their pwn-to-own 2018 exploit, where they found first RC in Safari, and then a sandbox escape via Mach IPC messages, and were able to get full RC on the system. So highly recommend reading this blog post if you're interested about anything in this talk. Okay, so we're identifying an attack vector. We've kind of slimmed down the number of Mach services that we're looking at. Now we need to find an entry point, which is a way that we can send our inputs through that attack vector into the system. So we know that the Mach message function is used to send Mach messages from one process to another. So kind of my first idea here was, why don't we just go ahead and hook onto a process, and then whenever it goes to send a Mach message, we'll just do some dumb bit flipping on the message body and see what happens. So that's exactly what I did here. You can see the Mach message function is sending by land. That's going to be processed by the kernel, sent to the message handler, and then the receiving process is going to say, okay, that sending process said by land. Now here, what I started doing was hook with LLDB, the Mach message call, and then mutate that message body to by C, and then the receiving process is now going to get that message and process it accordingly. So the pros to this approach, it was simple, and it was pretty similar to what we're going to expect in maybe our end exploit, because we are probably going to need to use the native Mach message send function call. But it was very slow. I was at the mercy of whatever application I was hooked into to send messages, and sometimes messages don't get sent for a while. So as far as being efficient at fuzzing, this was a really bad approach. There were also a lot of points of potential failure along the way. You know, we're getting it processed by the kernel, we're using LLDB. There were a lot of ways it could fail. And then probably the biggest problem here was we were dealing with two different process spaces. So one was the sending process, which was actually calling Mach message. The other was the receiving process. And getting code coverage, which I'll talk about in just a minute, proved to be pretty difficult in that specific scenario. And then it was difficult to determine which message actually caused a crash, kind of because of that two different process spaces. So I went ahead and decided to shift gears a little bit. I thought, okay, instead of waiting for Mach message send to be called, what if we just write a program to call it ourselves? Then we don't have to be at the mercy of the sending process. So I did that. I wrote a program that would just loop and continue to call Mach message. And then I thought, okay, what if we actually go a little bit further? We're still having our messages processed by the kernel. What if we actually just called the message handler directly? And I like to refer to this as getting close to the system of interest. So we're getting really as close as possible as we can to that message handler and saying, here's our input. The pros of this is it becomes much, much faster than we saw before. It's also in the same process space now, which makes it a lot easier for instrumentation and code coverage. And then it's much easier to know which input caused a crash and then replicate it. There are a couple cons here. One would be it's a bit different from the end exploit. We're not actually going to be able to directly call this message handler from Safari, for example, because it's not an external API that's exposed. We also might need to invoke initialization routines on that receiving process before we can just call its message handler. But this approach proved to be much more useful for me. Okay, so we've talked a little bit about identifying that attack vector and how we might actually want to send inputs to it. Now let's talk about generating a corpus of inputs. So we have that attack vector. Now what do we send to it? In fuzzing, sending totally random data, it really depends on what you're fuzzing, but in the case of Mach messages, sending random data is not likely to produce meaningful crashes. And that's because there's a lot of exceptions that are handled and input validation that occurs in Mach IPC. So we're probably not going to be successful just by piping dev view random into it. We need to identify examples of valid mock messages first, or build a corpus. Before I talk about this, I just want to mention a couple of things. When you start debugging on macOS, what you're going to need to do to generate this corpus and fuzz, I would highly recommend setting up a virtual machine, because when you start attaching to processes with LLDB, you're going to need to disable system integrity protection. You're probably also going to want to disable the built-in report crash daemon, as well as some of the native sleep functions that are enforced by default. And there's a really good DEF CON talk from a couple of years ago that I linked here, which provides kind of everything you might want to think about if you're fuzzing on macOS. Okay, so let's get back to generating that corpus of inputs. First, we want to find a mock service of interest. So in our case, one of the processes that I saw accessible from sandboxes most commonly was the core audio daemon. This is COM Apple Audio Core Audio D. It handles all interactions with audio hardware. It also performs a lot of privileged operations, and as I mentioned, it accepts mock messages from a lot of different processes. So one of the things I did was I attached to Core Audio D, which was the binary which the Core Audio service launches upon startup, and saw that it loaded the Core Audio framework, which you can see in this first image here. And so I was like, okay, I'll pop that into IDA Pro. We'll start looking at actually how these messages are handled. If you try to do that, though, you see that the Core Audio framework binary does not exist on the file system. And this kind of threw me for a loop for a little bit until I figured out that starting with macOS Big Sur, most framework binaries are actually not stored on disk. They are stored in what's called the DILD shared cache, which is a way that the macOS optimizes using these framework binaries, but they're not just sitting on disk. Thankfully, there is some useful tools to extract binaries from the DILD shared cache. I've linked to one here, and we can actually fully recover those with a lot of symbols still intact. So this was very helpful. So now I had the Core Audio Framework binary, and I could start performing some static analysis on it. Okay, the next thing was finding the function which handled the mock receive functionality. And you might have been wondering, didn't I say in the beginning that the mock message function was used for sending and receiving? This is true, and initially I thought I could just hook onto this function and see all the messages incoming. But actually when you're receiving a message, in order for kind of non-blocking I/O to occur, it traps to the kernel. And so if you want to use mock message to look at received functions, you actually need to kernel debug or write a kernel extension. And so I looked into this a little bit. It's a bit annoying, though, because you have to use 2 machines on macOS to kernel debug. And you're also seeing every single mock message that's sent on the system, and it's tough to isolate the target process that you want to look at. So I was wondering, is there an easier way that we can actually figure out the function that's receiving mock messages? And it turns out there is in a lot of cases. So Apple provides this thing called the Mach interface generator, otherwise known as MIG. It's an interface definition language compiler, which means that it abstracts a lot of the Mach IPC layer away and allows you to create stubs, which you can call, and then it handles kind of all the Mach IPC under the hood for you, which is nice. So this diagram shows a little bit about how this works. You specify a definitions file, and then you're able to define stubs and how they should be handled. It's very high level. And then the MIG compiler will take care of all the Mach IPC stuff under the hood. So I thought, okay, this is cool. What if I just look for these MIG subsystems and then try to hook onto them? This is actually what the RET2IO team did in their research that I mentioned at Pwn2Own. There's a pretty useful Hopper script that I kind of converted to IDA Pro in order to detect MIG subsystems within a binary. But you can also just look at symbols and kind of look for subsystem in most binaries in MIG, and you'll pretty quickly determine where the MIG subsystem is. So once we do that, here's an example of one of the subsystems I spent a lot of time fuzzing, and hopefully you can see this screenshot okay. But at the top of the function you see here, this is the HAL's MIG server subsystem. We have two inputs to the function, and they're both Mach message header T types. So that first input, which is going to be the RDI register, is our incoming Mach message. And then that second input is actually the one that's going to be returned to the sending process. So this process handles incoming ones, and then it sends a response back to the sending process. Okay, so that incoming Mach message is then going to be parsed. And you can see here that the server is parsing out the message ID that's being sent, which is one of the fields you can send in a Mach message. Then it's getting the offset to the MIG server subsystem that we looked at the slide before. And then it's indexing into that. So it's a function lookup table based on the message ID. And then it's calling the desired function. So this is pretty typical RPC-like functionality. We're parsing a message ID, getting a function from that, and then calling it. And you can see here are the RPC functions that were actually exposed by Core Audio via this MIG server subsystem. So quite a few. They all start with _X, which makes it easy to identify them. And here's an example of opening the Core Audio system. Okay, so now we know actually what function is receiving messages for a process that we're really interested in. And so I wrote a simple script here to just hook on to that message handler that we found using LLDB, and then just start spinning out that RDI register, because that's going to contain our Mach messages. So this is just a quick video. Hopefully you can see it okay. We're just looking first for the Core Audio daemon process so that we can attach to it with LLDB. Then we're using this Mach message dumper script to specify the process ID, then the library or the module that we care about, the Core Audio framework, and then the function, which is that HAL MIG server that we talked about. And then we should start seeing messages being dumped and saved to the system. And I would commonly open up like YouTube or a music player so that I could generate more traffic by interacting with audio devices. You can see when we opened up Apple Music there, we started getting a lot more messages. And so people will write custom scripts to generate traffic on a system in order to see more messages. So this is a pretty common technique. But doing this, we were able to save a lot of valid Mach messages that we could then use to fuzz. Okay, so we generated a bunch of valid inputs. Now we need to figure out, or we need to write code to actually send that to the message handler. And to do this, we use what's called a fuzzing harness. So this is code that you write that allows you to send input through an attack vector. Or at its core, it's just calling a desired function. So this is often pretty simple to do on Windows. I'm sure a lot of you have used load library and get proc address. On Mac OS, it's pretty similar. There's the DLOpen API, which you can use to load a specific dylib. And then there's the DLSym function, which you can use to get a specific offset for a symbol within that library. But the specific method that we care about, this MIG server function, was not actually externally accessible or exported. So I ended up having to write my own Mach symbol parser, go through the whole symbol table, figure out the specific offset, and then call that offset directly. So that's a little bit of a talk for another time. I'm hoping to open source that process after this talk. Still going through some approval processes at Google, but was pretty interesting to work through for me. So here's how this works. This is the harness. We're specifying here the core audio framework as our library. We're specifying the function that we want to attack, our attack vector, the MIG server. And then we're passing in, this attackf flag is passing in a specific input that we want to send to the message handler. And you can see here, the first output there is the Mach message that we're sending. We call the function, we actually get an error, and then we get a returned Mach message from the receiving process. So we've built a harness, so now we can send messages to the function we care about. Once we have that, we can then use a fuzzer. And a fuzzer is just a program that generates inputs that will be sent to a system and monitors for crashes. So with this fuzzing harness, what does this actually look like? Well, step one is going to be taking in our inputs, which we have generated in our corpus. We're going to pass those to the fuzzer. The fuzzer is going to start mutating those inputs. It often does so randomly, but there can also be kind of additional steps you can take to do so more intelligently. It's then going to send the message through our fuzzing harness directly to the message handler. And then the fuzzer is going to look at, okay, was there a crash that occurred in that receiving process or no crash? If it's a crash, it's going to save the input because that's a good input that we care about. If not, it's going to continue to modify that message and maybe move to a next input. So you can do this for as long as you want, and you generally have to do it for a long time to generate interesting crashes, in mature code at least. So let's take a look at this toy example here, though. The process that I just showed you here of just randomly flipping bits might not be super useful in a function like this. If you look at what's going on here, we're processing an incoming string, and we're first looking, is it greater than 3 in length? We're then looking, okay, is it equal to length 3? And then we're looking, is the first character S? And then finally we're looking at, is the string secret? If so, we dereference a null pointer and we crash. This process that we just talked about is going to have a really hard time of finding that crash because there's so many different conditions and we have no insight other than the program crashed or it didn't. And for this reason, we need what's called code coverage. And code coverage is tracing a program's execution flow in order to identify new code paths. So what this means is that instead of just looking at was there a crash or was there not a crash, we also are looking at did we go down a code path that we've been down before, or did we actually just find a new code path? And if we found a new code path, that's actually a really interesting input for us, and we want to save that back to our corpus and start fuzzing with it. So this is a very commonly used technique in fuzzing, and it'll increase your success rate by a very large margin, just because you're able to see actually what's going on in the receiving binary. So how do we determine code coverage? First, on the right, this is actually one of the targets that I was fuzzing, and you can see the code coverage for this specific function. The green nodes are code paths that we've hit, and the white nodes are code paths that actually haven't been explored yet. So you can get a pretty good idea just by looking at this what you still need to fuzz. And you can look at sort of these branch conditions and see why am I actually not getting to this part of the code? And this can really help you increase the efficiency of your fuzzing and know that you've kind of covered all code paths. So for actually getting code coverage, how do we do this? If you're fuzzing something with source code, it's pretty easy. You can use AFL++, libfuzzer, or gcov, and actually add in these libraries directly into the source code to output that coverage information. But it becomes quite a bit more difficult when you're doing black box fuzzing, which is what we're doing here. So we don't have the source code for these Apple system binaries. And so to get that code coverage, we actually need to use dynamic instrumentation. So this is using either Frida, which is a very common dynamic instrumentation framework, Or in my case, I decided to use something that my colleague at Google wrote called TinyInst. But what both of these programs do is they essentially attach to the receiving process, and they just look at the execution flow and print out sort of where we're at in the process. And it'll then be able to tell you if you're reaching a new area of the process that you haven't seen before. Then once you have that code coverage information, you'll load that into a analysis program, which the one you see here is a really commonly used one for IDA Pro and Binary Ninja. It's called Lighthouse, and it works really well. It'll highlight exactly where you've been and where you need to go. Okay, so next, I got into actually fuzzing our end service. There's been a lot of build up to getting here, and I was pretty excited to get started. The fuzzer that I used here, you can use whatever fuzzer you like. I used the Jackalope fuzzer, which once again is written by Yvonne Fratrick, one of my Google colleagues. And I decided to use this just because I really like the options it exposed. And it was simple for me to use. I could also ping him if I had any questions, which was the biggest reason. One thing that you can do and that you definitely should do is enable Apple's guard malloc, which is very similar to address sanitizer on Linux. It places restricted pages around all memory allocations so that if there's maybe a memory access off by 1, you'll see those very granular memory accesses that might be disallowed and lead to something like a buffer overflow. Then I used TinyInst, as I mentioned before, to perform dynamic instrumentation and dump that code coverage information, and then Lighthouse to interpret the code coverage. And here is a little bit of a screenshot of just running our fuzzing setup. So at the top, you see a whole bunch of garbage that's being passed into this command. Basically, we're just specifying our fuzzer, Jackalope, specifying our corpus of inputs, telling it that we want to use the custom fuzzing harness that we wrote, and then specifying that the module that we want to instrument to get code coverage. This first sort of highlighted red area is just showing that guard malloc has been loaded into this process. So all allocations are going to be placed on a 16-byte boundary here. That's great. And then actually in this screenshot, we see a crash that occurs. This was just a C++ exception, so it wasn't anything super interesting because it was handled by the receiving process. But we do see that when that occurs, there's instrumentation that is produced by TinyInst, and we can see exactly where that happened and how we got there. Okay, so once you start fuzzing, I mentioned before, you want to regularly check your code coverage because we can learn a lot about where the fuzzer is and isn't getting to. And a great goal to have in fuzzing is just to cover as much of the binary as possible. So hit as many code paths as you can. If you've covered all code paths and you haven't produced a crash, you can be pretty confident that it is looking quite nice. And this is why open source fuzzing projects like Google OSS Fuzz are commonly outputting the amount of code coverage that they've achieved and trying to always up that number. Okay, and the final step here is going to be identifying relevant crashes that you're able to produce while fuzzing. Not all crashes are created equal, and some are likely not exploitable based on basic heuristics you can look at. So ones that you really care about, a crash on write, a crash on execution, an illegal instruction crash, corrupting the heap, or a stack trace that contains like a memory allocation or free function. Things that you might not care as much about, a crash on read, although this can be used to leak memory, which can be useful in building exploit chains. A handled exception, a null pointer dereference, or a stack recursion error. There's some useful tools that you can use to apply to the crashes you're generating and triage them. Apple provides a tool called Crash Wrangler, which is a bit outdated, but it does still work well to kind of look at some of these heuristics and tell you if you should worry about a specific crash. There's also a good project on GitHub called CrashMon, which uses LLDB to do the same thing. So highly recommend using those tools to speed up this process. One really important thing when looking at crashes is whether you're able to reproduce that crash. Oftentimes, you'll hit a very specific use case, and you won't be able to reproduce a crash, which is very frustrating. But some of that is a very important thing that you need to keep in mind. So you should be able to run that input through your fuzzing harness again and continually generate that crash in order to have what will likely be a reliable exploit in the end. Okay, so a couple takeaways and just talking about what we've covered. Really hope this crash course on fuzzing and Mach IPC mechanisms was useful for all of you. We went through quite a bit of material talking about the attack process and things you might want to think about as you do some of this fuzzing research yourself. Identifying an attack vector, generating a corpus of fuzzing inputs of known messages we can send, writing a custom fuzzing harness, actually fuzzing, producing crashes, looking at code coverage, and then triaging those crashes. Hopefully you also saw some of the mistakes that I made. That is something I really want to underline here, that it was not always easy or that I knew what to do next. And this is just a common thing in vulnerability research. But it's also a lot of fun because you learn a lot in the process and you're constantly getting better. And I really hope I've inspired you to do some vulnerability research as well. As far as next steps for this research, I want to continue increasing the code coverage of these Mach IPC handlers that I've been fuzzing. One of the things that I've started to implement is stateful Mach message fuzzing. So it turns out the message handlers sometimes care about the order in which Mach messages are received. And so I've started looking at how do we determine the order in which to send messages to increase our code coverage. So that's some research that's still going on. Additionally, I mentioned when you're calling a message handler directly, sometimes there are initialization routines that need to be called before you can actually send a message. And so I'm working on automatic initialization of some of these Mach service binaries. I mentioned I'm going to open source my Mach message dumper and fuzzing harness. I apologize I wasn't able to get that approved by this talk, but it should be hopefully very soon. And you can follow me on Twitter or check out my blog. I'll be sure to update you when I release that. And then additionally, I would love to collaborate with any of you that are interested in this sort of research. Always looking for people to ping ideas on, talk about kind of new techniques or methods that you all have, and hopefully collaborate on research. So with that, thank you so much for listening, and happy to answer any questions you have. Yes, I did. Yep, I did do all the fuzzing within a VM. I used VMware. You can definitely use VirtualBox. I know people who have also fuzzed macOS with QEMU, although it's a bit of a pain to get set up, and there's some licensing issues with doing that. So VMware was a good process for me. You do need to run VMware on a Mac, which is something to be aware of if you want to go that route. That was actually just on this laptop, yeah. And then also had a couple of other Mac OS laptops that I was just running kind of overnight all the time. Yeah, you can definitely do this in the cloud too. It's pretty expensive, which is why I didn't go that route. But yeah, AWS, you can definitely start up a cloud server and run these types of things. Perfect. All right, I think we're at time. Thank you all again so much.